Good afternoon, YouTubers. Today is Sunday. It's a great day to do some studying, ballistic studies. Here we have a Glock pistol. It's going to fire a 9mm bullet, and here are the properties for that bullet. As I, search for them in the internet. The mass is about 7.45 grams. The bullet diameter is 9mm. The coefficient of drag is 0.295, and the density of air, because we're gonna consider drag. That's the important thing, that as we fire this bullet vertically, and the muzzle velocity is about 370. That according to the internet's Glock standard. So with that said, what's the story here? Well, the story will be fire here from Earth, and it will do this kind of trajectory, and then eventually will come down. And we know that the initial velocity is 370 as the bullet is fired, but eventually it's going to reach the top height, and the velocity there will be 0, and then the bullet will come down. And the question is, what is this velocity? That's the impact velocity when the bullet comes down. Now, you can work this problem, basically, I would say there are several strategies to work this problem. The one that I found easier for this is, like, for example, if we're going to consider drag, so let's do in two parts. First part will be the bullet going up. I will call this part first part, and then the bullet coming down, I will call that the second part. And that's the idea. Now for the first part, what's happening here is you have a bullet. I'm going to shape a bullet something like this, and that bullet is going up with a velocity, and however that bullet is going to experience, as it go up, the force of gravity. That's going to be mg, but it's also going to experience drag force, so Fd. So those two forces, as the bullet is going up, it's going to experience these two forces that are going to slow down eventually until the bullet reach the maximum height. So with that in mind, if we work out the second Newton's law here, that would be that the sum of all the forces in the y direction, we're going to consider this y, there's no x, so and we're going to consider positive up. That means that this force, the force of gravity, mg, which is the weight of the bullet, minus the force of drag, and that will be equal to mass times the acceleration of the bullet going up. So that's the equation that we have. Now here's the story. We also know that acceleration by definition is the change of velocity with respect to time, but we also know that distance, the change of distance with respect to time, that's velocity. If we divide this by this, we're gonna get a over b equal dv over ds. If we separate variables here, we're gonna have a ds equal b dv. Now here's the nice thing about this kind of I would say third version of the first, when you use 1 and 2. On this third version, I have ds and I don't have time. This time is not involved here. So this is kind of nice because I don't need to know the time. I only need to know at least or two limits on velocity or two limits on the distance, and in either side. But what I really know at this point is two limits on the b side in the velocity versus one limit here, because when this whole thing started was at s equal here on the first part, what I'm saying is s equals 0. So basically, when we separate variable here, we're gonna have something like this: v over a dv. Now, what is a? Well, that's easy, because a come from here. A is equal mg negative minus fd. Let's introduce the definition of d. That's going to be 1/2 the coefficient of drag times the density of the air times the area. This is 1/2. This is look ugly. 1/2 coefficient of drag, density, air times this velocity square, and that we divide that by m, because that's what I'm going to be doing here. Divide by m, we end up that a is equal negative g minus 1/2 coefficient of drag, the density of air times the area times the velocity square over m. That's kind of interesting because all of these are constant. So we have 1/2 coefficient of drag, density, the area of the bullet based on the diameter of the bullet, divided by the mass of the bullet. So all that is a constant. I can always set something like this: minus g minus k b squared. So now we have a nice a nice equation here, the acceleration of the bullet that can be plugged here, but it's in terms of v. So that end up being ds equal v over, I can take the negative out, and so end up this being g plus kb squared, and now dv. And as I was saying before, I have the two limits on this side. What are the two limits? If we integrate both sides, when the distance is 0, that's when I fire the bullet. That's 370 on this side. When I reach the maximum distance s, that's going to be when this limit, the upper limit, is 0. Now, most people don't like to integrate like that. I don't care. If you prefer, I can switch here the limits, so another negative will pop out. Let's put minus minus. This is minus, but I'm going to change the limit here, so it's going to end up with 0 and 370 v dv g plus k v squared. So in this left side, the integral of ds is s, evaluated between 0 and s. Obviously that's going to be s, equal minus minus, that's positive. So we end up having this integral from 0 to 370 v dv g plus something got I don't know, something sort of disappeared on me, but I think that was this number here. Sometimes my surface disappears things randomly, so I guess that it's getting weird here. Anyway, so from 0 to 370 g dv g plus kv squared, and that's the integral that we need to deal with. Now let's see where we are. We need to integrate this, but before we integrate that, how about we calculate k? K is 1/2 coefficient of drag times the density of air times the area of the bullet divided by the mass. So we substitute number, that's 0.5. Coefficient of drag, it was on this table. Coefficient of drag is 0.0295. 0.0295. So if we get all that numbers, times the density times the area. The area will be based on a 9mm bullet. That's going to be pi by, now change the 9mm to meters, right? So it's 0.009, and that's going to be square, and all that divided by 4. So we got the area and the whole and the mass. And the mass, this m here, is about 0.00745, because it has to be in kilograms. In the table was grams, as shown here. Mass 7.45, so it need to be in kilograms. So with that, k is about, put a calculator here. What? 1.543. Interesting. 1.543 times 10 to the minus 3. Now the units of that k, let's see. This doesn't have unit. The 0.295 doesn't have unit. The density, yes, that's will gonna be kilograms over meters cube. And this has area, meter square. and I have kilogram under here. Kilogram cancel out, this cancel out, so eventually it's going to end up 1 over meter. So this value is m to the minus 1. So that's k value. We got that. All right. With that said, let's get this, integrate this. So we're going to integrate this from 0 to 370 v dv g plus k v squared. Now that integral is equal s. So basically you solve this, you have the distance, the maximum height that this bullet will reach until the velocity reached to 0. From it was shot at 370 meter per second, so it's going to end up 0, and that's where it will return back. Now so that's what we divide the problem in two parts. The first part is shooting the bullet vertically up with considering the effect of drag on the bullet. Now to integrate this, let's do what we do in calculus. Basically, let's do a substitution, make life easier. U equal g plus kv squared. So du is equal, this is a constant, so it's going to be 2kv dv. So it's interesting, v dv is already here. So this integral will look more like this. v dv equal du over 2k. Now, if we substitute, what we already know for this in a general sense, what we are saying is that v dv is du over 2k, but then what is this? Oh, here in the denominator is u. So that integral, which was kind of weird at the beginning, end up being very, very simple. Du over u, that's log of u, so we end up 2k by the log of u, which eventually is just 2k over the log of u, but u is g plus kv squared. Now, so this integral end up being like this, so the only thing that I need to do is to evaluate the limits. So let's write this from 0 to 370. Now if I do that, s equal 1 over 2k, can take that outside, log of g 9.81 plus k. I don't know, k is a huge number here. I mean, I'm kind of debating whether I'm going to write all that, but I have to plus 1.543 times 10 to the minus 3 times 370 squared, close that parenthesis, minus when v is 0. So that end up being log of g, that's going to be minus log of 9.81, close that bracket. So the final s equal 1 over 1.543 times 10 to the minus 3 and here's the 2 as well. I don't miss the 2 and the 2, these 2 times, if I simplify this, some of the logarithm nice rules that we have, that's going to be 9.81 plus 1.543 times 10 to the minus 3 times 370 square and all that over 9.81. So let's see, let's pull the calculator here. S equal the log of 9.81, 1.543 times 10 to the minus 3 times 370 squared, close that parenthesis. Now divide by 9.81, close that parenthesis, by the log of that, divided by 1.543 times 10 to the minus 3 divided by 2, and the final distance is s equal 100.938 meters. Bingo. So what that means is that the bullet, when it's fired, as demonstrated for the first part, that bullet eventually will reach a final distance of 1009.38 meters. That's the first part. So now that we know what is the distance that the bullet covered, then we can jump to the second part. What's going to be on the second part? Well, the bullet will change direction. The bullet will start to look like this, And so what's interesting, mg now is acting in the same vector as the velocity, but the drag continue to be a drag, right? So it's against velocity. That means that the force of drag will be here as the bullet is coming down. And this is the second part of the analysis, and this second part is the one that will give us the velocity or the impact velocity. All right, so what's the story? The story is that the bullet will start from here, from the top elevation, and will come down until finally it reach a value of s equal 1009.38. So that's the story. So if you do the analysis, the force analysis, you will find out that in this case mg is positive, because I'm gonna assume that as we go down, we gain the bullet will accelerate coming down. So that means mg is positive, but the drag is keep on the negative, so that's will be minus fd equal. So those are the only two forces involved, this one and this one, and that's going to be m times a, through the second Newton's law. Now, as we did in the first part, what we know is that acceleration times ds equal v times dv. And that's interesting, because basically why I'm jumping to this one, because this one will not involve time at all. I don't need to know the time to find out what would be the here v impact. But what I need to know is, at least for the ds part, I need to know two parts. Like for example, the two limit, s equals 0 at the start of when the bullet is coming down, and then eventually what was the distance that is covered. Oh, I know those two limits, 1009.38. So using this equation will serve the purpose to very quickly find the velocity of impact without knowing anything about time. I mean, you can ask how long it takes the bullet to go up and then come down again. You can do all that, but if the question is only about what is the velocity of impact, and why is that important? Because there's many there's many issues about when people shoot bullets at the air and then they will come down, and whether the bullet has enough kinetic energy to kill somebody. And and there has been many accidents, and many people have already been killed by this type of air run behavior of shooting bullet to the air. And when the bullet come down, it might not have all the kinetic energy of the bullet when it's fired in the first place. When bullets fire here, it has a lot of kinetic energy because it's traveling at basically at 370 meters per second. But still, when that bullet comes down, have kind of a pretty decent amount of kinetic energy that will hurt somebody badly, and depending on whether it's in the head, the skull, that would be bad. So we're going to try to find out what is the velocity of impact and to measure that kinetic energy of impact. Well, with that said, let's work this out. So I have, again, the main point here is to know what is A. Well, A comes from the force balance, so that would be mg again minus fd, and if I use this 1/2 coefficient of drag times the density of air times the area of the bullet, and this time the velocity square equal ma. If we divide by m both sides, we end up with something that looks like, we already know what it's going to look like, but there's a change in sign. The g part is positive now, but the drag still the same now. Again, all this here can be combined into one constant that will be k b squared equal a. So with that said, this is straightforward. So we have ds equal v over a dv, but now a is in term of b, and that makes life easier, because then we have v dv over g minus kb squared All right, so now the limit for integration is when the s is 0. Remember that now I change a little bit the scale. Is s0 mean is here at the maximum height or elevation, but then as the bullet drops toward earth, that's when it's gonna reach the maximum distance that I already have. That's 1009.38. So this is the final. This looks a little bit. Let me delete this. So it's 1009.38, but it starts at 0. So this left side, the integral of the left side is s evaluated between 0 and 1009.38, which eventually is 1009.38, and that has to be to the value of the integral of the right side. So that will be the integral from 0 speed, and this is 0 here, to a velocity v, I don't know what it is, v dv, g minus kv squared. So as I did before, this is straightforward. If we do substitution, u equal g minus kv squared, du equal g is a constant, minus 2kv dv. Now v dv is here, so I end up with the minus 2k now. So meaning that my integral in general form is v dv, but v dv is du over 2k. Don't forget the negative right here. Now, what is u? U is this definition, so u is here. So we end up basically with the same integral equation like last time, except there's a negative here, 1 over 2k times the log of u. Now, what is u? Is this. So if we substitute back this integral of v dv g minus kv squared, kv squared from 0 to v is equal minus 2k times the log of u, but u is g minus k b squared, and all that has to be evaluated between 0 and v. So end up being negative 1 over 2k times the log of, let's open here, so it's going to be g minus kb squared minus the log, when this is 0, so minus g, close here. So this negative here, and if you combine with the logarithm rule, then end up being like positive 1 over 2k, but then log of g over g minus kb squared. This is getting pretty much done. And now the story here is that we need to put this equation in terms of b, and that's all that is equal s, and s is a value of 1009.38. so if we break this by, if we work the whole thing by against v, that end up being something like this, 1009.38 times 2k equal the log of g over g minus kv squared. Now let's call this, for the time being, any letter. Let's call that let's call that a, just for this time, for the sake of the argument. Let's call that a. So you take all those two sides and elevate that to the using the exponential. That means that a to the a is equal g over g minus kv squared. Now e to the e times g minus kv squared equal g. So we get g times e to the a minus e to the a kv squared equal g. So we need to break against this guy. So e a kv squared, that's going this side, and this is going that side, is equal g e to the a minus g. Getting better. So this go this way, that's why it's positive, but this go that way, that's why it's negative. Now I need to break against that one. So b squared equal g, I can take that g out, e to the a minus 1. This time this will be this and this one. And all that divided by e to the a k. Alright, so this is pretty much done. So that means that the impact velocity is going to be g over, I can certainly put this here if I want to. I'm going to leave the g and the k out, but then going to put e to the a minus 1 over e to the a. It looks like this. Make life easier on the math. And all that has to have the square root. This is b squared, so the square root of that means that b equal g over k. Now this over this, that's 1 minus e to the minus a. And that's the only math that we care. Now let's see. Now let's put some numbers now and let's see how this works out. K is equal again, what is k? 1 point was evaluated before. K, same as last time. Wow, where is that k? Oh, 1.543 times 10 to the minus 3. So k is 1.543 times 10 to the minus 3 meters to the minus 1. And then what is letter A? The letter A is equal here. That's the, just to make life easier. Letter A. Letter A is here. Is 1009.3A times 2 times K. And so let's see how that will end up being. 1009.38 times 2 times 1.543 minus 3, that's 3.11. 3.12, and now I have that. So eventually B is equal G 9.81 divided by K 1.543 times 10 to the minus 3, and that whole thing is 1 minus e to the minus 3.12. So V equal So the final velocity is 77.94, I would say basically about 78 meters per second. So let's get this clear. So the bullet was fired, and then the bullet eventually returned back. I'm doing kind of a long parabolic path here, it's not right, but just to get your idea. So the bullet was fired at 370 meters per second, eventually reached a maximum height of 1,009.38 meters, and then returned back. but here the impact velocity end up being about 78 meters per second. So the question is, will this be dangerous if you get hit by a bullet that is at 78 meters per second? And most likely the answer is yes. It might not have enough kinetic energy, but there's a lot of study being done that a bullet at this, a certain speed can be dangerous. So I'm back. I was doing some research about what's the minimum energy required for a bullet to cause some damage, and that minimum speed seemed, well, not the speed, actually the energy, it's a number. I would say I will average that number. That average energy number will be about 20 to 30 joules. So if the bullet is within that range, it will cause some damage. I mean, let's put it this way. If you are hit around your temples, you are dead. Basically, or through an eye, you are definitely dead. If it hit you with this amount of energy through your skull, which is the hard part, not the soft part, the hard part, you might survive because it will crack your skull. Bad too. I mean, what I'm saying is, even let's calculate what's the energy of this, and let's see whether it falls within this number. Anything above 30 definitely will kill you. In fact, you can compare the amount of energy when the bullet is at 370. Let's do that. When the bullet is at 370 versus when the bullet is at 78. So let's make some calculation. So 1/2, the kinetic energy is 1/2 mass times the velocity squared. So that would be 1/2 times the mass in kilograms. Is 0.00745, if I remember that right. Time 370 square, and the other one, this one here, will be 1/2 times 0.00745 times 78 square. So let's grab the calculator and let's see where our energy falls down to. So wow, 509.95 joules. A lot, way a lot at these minimum numbers here. So definitely you're hit by a 9mm bullet, and you escape, alive. It's a miracle. Obviously, depending on where you hit you in your toe, then you might survive. But if it hit you in any critical area, it will cause very serious damage. Now let's look at a 78. What's gonna happen at 78? Let's see. The number is interesting, 22.6. So I would say basically 23 joules. So it's right within the critical zone, I would say, to cause serious damage. So a bullet coming down and landing back on you on top of your head on the soft spot, it will kill you basically. Around the temple will kill you, through an eye will kill you. You are lucky if it hit you someplace else, you might survive, but it's still, I would say, quite deadly, even at this low speed of 78 meters per second. Well, the only thing that I have to say at this point is, people that are happy triggers firing to the sky, definitely it's a no-no. When that bullet come back again, it will cost, I'm talking about a small bullet, a 9mm bullet, not thinking of anything else, because then you have to do the analysis. But you can imagine a bullet that is a little bit heavier than a 9mm and will cause serious damage. So that's the bottom line of this. Definitely it's not the speed of what the bullet came out to when the bullet was fired 370 meters per second and then it returned at 78. when it hit back again, but still with enough kinetic energy to cause some serious damage. That's the end of it. Have a great day. Bye.